just have to flip it if you want, yeah.
Yeah, I'm just thinking, then you can just sit here and then you can look at it.
Yeah, but my problem is my
Video's
movies.
not embedded,
Yeah,
so
they're
you
not
gotta start
embedded,
them.
so I've got to start them, yeah.
Buenas tardes y bienvenidos a la Real Academia de Ingeniería. Good afternoon and welcome to the Royal Academy of Engineering of Spain. We are fortunate today to have this session on the space, and it will start by one member of our academy, Professor Amable Liñán, who will do an introduction presenting the historical perspectives between the JPL and Spain. So, Professor Liñán has the word.
Well, thank you very much, Mr. President. For having me invited me to give a short talk about the relation between between JPL and Spain, and I begin by thanking our speakers today. General Larry James, Deputy Director of JPL, and Suzanne Todd, who directs the JPL Interplanetary Network Directorate. They kindly offered us the opportunity to learn more on the outstanding work that NASA, and in particular JPL, are doing on the exploration of the Earth and our solar system and beyond. I will not use the precious time in giving you the details of their impressive trajectories that you had the opportunity to read in the announcement of their talks. Let me simply say that General James' career was initiated in the U.S. Air Force Academy and includes Master of Sciences in Aeronautics from MIT. Suzanne Todd initiated her studies of engineering at Caltech and later at the University of Southern California. I must thank the President for the privilege of saying a few words of the benefits of the long association of INTA, our National Institute of Aerospace Engineering, and our aerospace industry with NASA and JPL. This association was initiated when Theodor von Karman, the founder during the Second World War and first director of JPL, came to Madrid in 1948, invited by the president of INTA, Esteban Terradas, to give a series of lectures on supersonic and transonic aerodynamics. Gregorio Millán, then a young professor of aerodynamics in our military school of aeronautical engineering, helped him in the logistics of von Karman's presentations. He was impressed with von Karman, with the knowledge that he had, and asked him to collaborate with him, together with Saul Penner, Caltech professor of propulsion, in extending the laws of fluid mechanics to account for the kinetics and thermochemical effects of combustion reactions. Von Karman felt that a theoretical multidisciplinary framework was needed for the appropriate design of turbojets and rocket engines needed for high-speed airplane and ballistic missiles. The collaboration of Millan and Penner with von Karman was soon initiated and fruitfully carried out with annual one-month visits of von Karman to Madrid and 3-month visits of Millan to Paris, where von Karman was spending half of his time as chairman of the AGARD. The AGARD is the advisory group for aeronautical research and development of NATO. And von Karman in 1951 gave a series of lectures in La Sorbonne, in the Institut Poincaré, with Gregory Millan as assistant on these equations that define the combustion processes. The lectures were updated by Millan with a combustion group created at INTA with the partial support by contracts with the AFOSR, the Air Force Office of Scientific Research, which ended with a monograph with the name of Aerothermochemistry, which was published in fact at the beginning of 1958 as an AFOSR report that had very wide circulation in the aeronautical laboratories of the US and Europe. I personally met von Karman for the first time in 1958 when I was a student, an undergraduate student at the school, and he organized in Madrid the first International Congress of Aeronautical Science. In this meeting, the top engineers and scientists of the world came to talk on the main problems involved in high-speed flight and rockets. 4 explorers were launched during that year, and including the first explorer that established the existence of the Van Allen belts containing the energetic particles trapped by the magnetic field of the Earth, which allows us to have life in the planet. Von Karman also helped to organize INTA to organize in Madrid in 1960 and 1961 a course on space technology with the top international experts in the field. He was also influential in creating our National Committee on Space Research, who joined in 1962 the ESRO, the European Research Organization. The collaboration of NASA and ESRO initiated also with the creation of a NASA ESRO fellowships. They were offered to promising young engineers to study and carry out research in the laboratories of the U.S. universities involved in space research. I was then a young engineer at INTA and went to Caltech for 1 year, which ended with an aeronautical degree, engineer degree there. Then I was witness of the early NASA INTA contacts for the deep space research station. I learned from 2 of the engineers of JPL that Manuel Bautista, later director of the Spanish leg of the Deep Space Network at Robledo de Chabela, would soon visit JPL for these contacts. they wanted some additional information on INTA and on my personal relations with Bautista, who had been my professor of aerial navigational techniques. When in the early 80s, Bautista was named director of INTA, his position at the Deep Space Network in Robledo de Chabela was covered by José Luis Fernández, his deputy director, was named for the position. Soon, José Luis moved to JPL to be involved in the association, the interaction of the space stations with the main programs, the growing programs of deep space exploration, so that he was involved in the Voyager, the Magellan, and other. When I came back from Caltech, I encouraged my brightest students to use the opportunity of the NASA ESRO fellowships. Thus, for example, Antonio Crespo and Chirivella, who were part of my first students of the class, or my first class in the University of Madrid, in our School of Aeronautical Engineering. They went to Caltech. Chirivella soon moved to JPL to be involved in the energy conversion system directorate that occurred at that time, and was involved in a variety of missions, especially to see the contamination by the attitude control jets of the solar cells and the sensors of the satellites. He developed a special, very efficient program to analyze that, and finally spent most of his active life there, Chirivella. Manolo Martinez Sánchez went to MIT. In a certain sense, I encouraged him to go there and to be our representative at MIT. And he, in fact, never left MIT. He became professor of propulsion and at the aerospace department, and has been involved in the design of especially electrical propulsion at MIT. Anyway, other people of our school, other bright students like Javier Jimenez and Manolo Rebollo, who is not here, but went also to use the NASA ESRO fellowships to go to America, and Javier Jimenez, when he came back to Madrid, was involved with IBM in the development of techniques, digital imaging techniques that were used to understand the coherent structures that had been developed found at Caltech, and then one of his students, Miguel Hernán, went as a postdoc to Caltech, but then was hired by JPL to participate in the Voyager program, and so that, and in particular in the redesign of the modification of the backup propulsion unit to receive the photographs, to accumulate the photographs that were going to be made in the passage through Uranus and Neptune, and to then send back to the information to the deep space stations, where they had to, so that they had to, these deep space stations not only receive the information from outside, but send the information to the satellites, and so that they have a very tough task. Anyway, another fellow, or a classmate of Javier Jiménez, ¿cómo se llama? ¿Quién era? Tu compañero. He went to... No, to USC. He went to USC, and in fact was involved in with Busey, who was involved in the Kalman-Busey filtering, and then used this for tracking, for following the parameters of the space vehicles, and so that he finally ended up in Darmstadt, in the European station that keeps track of this, and had been there for many years and was involved. So that the only one that didn't go to another member of our academy, that didn't use a NASA Aero Fellowship, because he was a very, very bright student. And I do not like the new policy of the NASA that was to send, to distribute the students to less important universities. And he ended up in Colorado, and in 2 years he got a PhD in the analysis of long-wave probes for measuring the plasma density and temperature. And then he ended up in the Princeton Plasma Physics Laboratory, and then at MIT with Prof. Stein. So that this relation was very, very fortunate for us, and as I say, it includes the development of aerospace science, not only engineering but science at the same time. And we are very happy for you to have come here to talk, and hope that we'll have another opportunities to hear you again in the future. Thank you very much.
Thank you very much, Professor Lignan. And it's now my pleasure to introduce Lieutenant General Larry James, who will talk to us about NASA and JPL, exploring the Earth, our solar system, and beyond.
Well, good evening. And buenas tardes. Thank you for allowing us to be here this evening. It is always an honor to come and work with our partners, and especially as you heard the history, a great partnership that we have had through many decades. And so we look forward to continuing that partnership and continuing to develop new capabilities and discover new things throughout the solar system and the universe together. So again, thank you for the opportunity to be here. You heard some of the history with Dr. Van Carmen and really beginning JPL. What I would like to do is first show you a little video that quotes Dr. Pickering, who was actually the first director of JPL and led us to Explore One, which you heard about, and hear his words in terms of the vision that he had for JPL, and really that vision has not changed, and also give you a sense of the atmosphere and the culture of JPL. So I'll just run this little video to start us off.
The long-range purpose of unmanned exploration of the planets is the development of technology which will lead to eventual manned exploration. Scientifically, our objective is to assist in answering two basic questions. What, if any, life forms exist on the planets? And how has the solar system been formed?
I think one thing that must set apart JPL from other places is the willingness to take on challenges.
Reaching for something different, searching for answers. JPL has this tremendous tradition of being the first to do many things.
This legacy of firsts allows you to dream big. And you feel like you want to keep that track record going. You want to contribute to the next first.
Encouraging that spirit of innovation, JPL has been able to continue to dare mighty things.
I don't know what can be more exciting than that. When you're creating the science, creating the knowledge, creating the technologies.
The quest is the culmination of all these efforts we're doing.
It's bigger than any one of us. It's a quest for all of us.
So I hope that gives you a sense of the excitement of doing scientific exploration and how really from the time of Pickering our mission has not changed, to seek if life developed elsewhere in the solar system and the universe, and also to really understand how the universe developed and evolved, as well as how our solar system developed and evolved. This is just a brief snapshot of really our history. You can see we really started back in 1936 with Caltech students and professors trying to develop rockets. That led to our development of rocketry in World War II, and then followed by Explore One in 1958. So JPL was created well before NASA, and when NASA was created, they brought JPL under the NASA umbrella as a federal funded research and development center. And of course, we currently do Mars exploration, planetary exploration, astrophysics, and a lot of Earth science. So all of these are a key component of the missions that JPL does today. So what I thought I would like to do is just kind of give you a snapshot tour of the solar system based on our current missions that we have operating around the solar system. And I'm not going to cover everything we're doing, but just some of the highlights. You heard mention electric propulsion. This is our Dawn spacecraft, which is using electric propulsion to operate in the asteroid belt. And here you can see an artist's rendition, of course, of the spacecraft, but that is an actual picture of the asteroid Ceres. Ceres is the largest asteroid in the solar system, and it really is a protoplanet. You think of asteroids perhaps as these rocky bodies, but Ceres was once a pretty active body. And in fact, if you look at some of the up-close photographs that we have taken with our Dawn spacecraft, you can see that a lot of activity has occurred over the years. The craters are fairly young because of the activity of movement on the surface, so the older crater markings have not survived. And then you have incredible structures like this on the surface of Ceres, which is really an ice volcano, if you will. That is a result of the the ice pushing up over time with the movement of the surface and the material below. Dawn was also the first spacecraft to visit 2 independent bodies. Before Dawn went to Ceres, it went to the asteroid Vesta, which is the second largest asteroid in the asteroid belt, and a rocky body, pretty much like you would expect an asteroid to be, and very different than Ceres, which again, as I said, is that protoplanet type asteroid. So a lot of excitement about this mission. Dawn is still orbiting Ceres right now. We've completed our primary mission, and NASA has approved us to continue that mission and continue to gather data about Ceres. So we will continue on as long as our fuel remains for the electric propulsion system, and that's probably another 2 to 3 years of exploration of that small planet. Juno is our latest planetary mission. This is the mission that arrived at Jupiter on July 4th of this past year, 2016, and really an incredible mission to understand the interior of Jupiter. Our previous mission to Jupiter, Galileo, was focused on understanding essentially the top of the atmosphere, understanding the moons that orbit around Jupiter, and understanding the weather, if you will, of Jupiter. This mission is really designed to understand the interior of Jupiter, because Jupiter is really the first planet that formed in the solar system. And by understanding the interior and how it was brought together, we believe that will tell us a great deal about how the overall solar system formed. And I have a small video here that was put together prior to us arriving at Jupiter, and really talks about the challenges of going to Jupiter with the intense gravity, the intense radiation, and all the things we had to deal with as we designed this spacecraft to operate at Jupiter.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. It just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system.
Biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation and the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about 1/3 of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we gotta go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion. JOI.
Nothing's really certain about what's going to happen.
Makes you want to see the movie, right? Well, the good news is that we were successful in that first mission pass of Jupiter. And as they said on the video, we passed within about 3,000 miles of the top of the clouds of Jupiter. That's deep inside the radiation belt. In fact, obviously we had to design all the electronics to survive that intense radiation. And as was said, it's a polar orbit, so we fly over the poles of Jupiter, the North and South Pole, which we have never done before as well. And we use that time when we're very close to turn on all the instruments, take all the measurements, and then we swing back out into a 54-day orbit. So every 54 days, roughly, we're coming in and making a low pass over Jupiter, collecting the data, then going back out, allowing the scientists to then analyze the data and determine what data areas they want to look at on their next pass. So been a very successful mission so far, and will continue to operate for a couple of years, and then NASA will assess if we continue on with the mission. I just thought this was kind of great. If you go back to the discovery of the Galilean moons, the 4 moons that Galileo saw and here sketched in one of his sketches with his telescope, and then as we brought Juno into Jupiter, we had this view of those 4 Galilean moons. So just an incredible historical feat, if you will, to actually now see with our spacecraft the moons that Galileo drew in his drawing using his telescope. We'll move on to Saturn. We have had the Cassini spacecraft in orbit around Saturn now for over 12 years, approaching 13 years. This has been an incredible mission to understand this really giant planet. The unfortunate thing is that we are running out of fuel on the Cassini spacecraft, and because we did not design it to be sterile from a planetary protection point of view, we have to crash it into Saturn in order to burn it up and get rid of any human microbes or anything like that that may in the future contaminate a moon of Saturn. So on September 15th of this year, we will be basically taking the spacecraft into the atmosphere and burning it up. But certainly prior to that, as we've reached this last year and moved closer to the rings, a lot of incredible discoveries. You can see the arrow pointing to that small object that is really very difficult to see, but that is actually a small moon embedded in the rings of Saturn that will soon be named. And then if you look at the things that we have been doing in the last year as we've gone closer and closer to the rings, we've had our first direct measurement of the ring composition with our instruments on board because we're flying so close. We've obviously had our highest resolution measurements and pictures of the rings of Saturn, as you can see there. First time we've actually been able to use our active radar to measure the rings because of our nearness. And then we've been able to get very close to the poles of Saturn and measure the aurora at a higher level than we've ever done. And then as we slowly lower the orbit and prepare to burn in, the last 5 periapses, if you will, the lowest approach, will actually be able to take measurements of the atmosphere itself directly, something we've also never been able to do. So between now and September 15th, it promises to be a very exciting time in terms of science and exploration and even better understanding of Saturn. This is just a quick video of a pass near the rings, what it would look like from the spacecraft's perspective. Hopefully that didn't make you dizzy. And again, just some incredible photographs of the moons of Saturn as Cassini has orbited around the planet. Now moving on to Mars. You saw in the brief video the landing of Curiosity. This truly is a selfie of Curiosity. This is not an artist's rendition, but we have a camera on the robotic arm that we can move around and take a series of pictures of the rover, and then we stitch all those together to give us this photograph. Curiosity has been operating on the surface of Mars now for about 4.5 years, and certainly Spain has contributed greatly to that with our weather system, if you will, that resides on the spacecraft, as well as our high-gain antenna, and that partnership will continue with our next mission called Mars 2020. But as you know, really the purpose of Curiosity was to determine if Mars could have been habitable in the past. What was it like hundreds of millions of years ago, and so on. And we can say with confidence today that based on the exploration we've done and the sampling that we have taken, that Mars was indeed habitable in the past. We have found evidence of neutral water. We have found evidence of large lakes and potentially seas on the surface, and just organics that reside there. So this is very important in terms of understanding what Mars was like hundreds of millions of years ago, and now what happened to it in those intervening years. I love this picture. We landed in a place called Gale Crater, and within that crater is a formation called Mount Sharp. And so we landed kind of in the level part of Gale Crater, and our objective is to gradually make our way up through that mountain area and understanding from the geological strata there the history of Mars. On the way, we have to deal with, obviously, you can see a very rough environment from the rocks there, and our rover drivers every day have to sort out the best path that they can send the rover on to accomplish our scientific objectives. And we also find large sand dunes there on the surface of Mars. And then this is one of our most recent pictures. Let me jump ahead to that, which, again, gives us a great view of those different geological strata that we want to climb up to. So you can see a hematite ridge, a clay unit, a sulfate unit, and our objective is to make our way through that valley and actually start climbing up, and we've actually started climbing up in that area to sample each of those areas that give you a different geological time frame for Mars and what happened over the years. So we have been approved to continue our mission well into the early 20s. Our nuclear power supply will probably start to dwindle in the mid-20s, but up until then, we hope that Curiosity continues to operate and do amazing science. Whoops. I did want to show this. This was taken from one of our Mars orbiters, and this is an interesting phenomenon where we see these wet areas that seem to run down into this slope of this crater. The scientists aren't quite sure what that is, but the best hypothesis today is that is some briny, salty water that is below the surface, but that is starting to seep up into the soil as the seasons change on Mars. So obviously a very interesting thing for the scientists, especially if you have surface water like that that could harbor some form of life, microbial life or something like that. So that will probably be an area we look to explore in the future to determine what is going on there. But we have our orbiting spacecraft around Mars as well as our rovers on Mars, each of them doing an incredible science expedition. As I said, we also do Earth science. So this is one of our latest missions that is observing our planet called Orbiting Carbon Observatory 2. And its mission is to understand the carbon dioxide cycle. So where is carbon dioxide being created on the Earth? Where is it being absorbed? And of course, that's very important to understand climate change and what is happening with the warming of the atmosphere and those sorts of things. And the next slide just kind of gives you a pictorial representation of the amount of carbon dioxide in the atmosphere, a model that we've put together based on the data from Orbiting Carbon Observatory 2. So you can see the colors in the red and the orange are high concentrations of carbon dioxide, and obviously the blues are the low concentrations. And you can kind of see how the oceans apparently absorb the carbon dioxide, and then the land masses produce the carbon dioxide in many places. And again, this is something we've never been able to do globally. We've never had a system that can map carbon dioxide absorption and creation on a worldwide basis. We've only had airborne measurements or instrument measurements at different locations around the globe, but not globally. So very important for understanding really the whole atmospheric model and how we can predict what the future will be like. So that's what we're really able to do with, spacecraft above the Earth, give us that synoptic view of the Earth and all that's going on. As I said, JPL operates in 4 areas, really understanding Mars and exploring Mars, understanding the planets and understanding how the solar system formed, looking out beyond the solar system into the broader universe and understanding how it evolved, and also understanding are there other planets out there. And then finally, as you saw, really studying our Earth. So I'm just going to give you a brief snapshot of some of the future programs that we have in that area. As we go back to Mars, this is our next Mars mission called InSight. InSight is a joint mission with the French and the Germans, which will study the interior of Mars. We've really never had any instruments on Mars to help us understand the core of Mars and what is going on below the surface of Mars. So InSight has 3 very sensitive seismometers that will allow us to very precisely measure any movement of the surface as well as beneath the surface. And then it also has a heat probe that will basically pound itself several meters below the surface and go deep enough that we can determine the core temperature of Mars. So those are the primary objectives, is to understand what is the core like, is it still active, is it still hot, and those sorts of things, and does it drive things on the surface. This mission will launch in May of 2018. And then our next Mars rover, we have not given it a name yet, but it's Mars 2020. And again, we continue to partner with Spain and INTA in developing the next generation of the weather platform, if you will, as well as the high-gain antenna. And so we're looking forward to all of that coming together. That will launch in 2020. In fact, over the next couple of weeks, we will conduct our critical design review for this mission and then continue to move forward with development and ultimate launch. One of the other key objectives of this mission, in addition to new instrumentation to find life, if it exists, is also to take samples. So we will take samples and put them in a small vial, if you will, metal canister, and leave them on the surface for eventual pickup by another mission in the mid-20s and return to Earth. So we call that Mars sample return. So we're in the middle of designing that sample system that will very precisely capture a lot of different core samples and keep them intact, so the scientists, when they come back to Earth, can examine the strata in the sample and understand that particular sample. So that is really a key objective of this Mars 2020 rover, is really the preparation for samples that will come back to Earth in the mid-20s. Europa is our next planetary target. Europa is one of those moons of Jupiter, one of the larger moons of Jupiter, but the interesting thing about Europa, it is a water moon. You see the surface there, that is an ice surface, but beneath that ice, we believe, is 2 to 3 times the amount of water that the entire Earth has. So that's how much water we believe is below the surface of Europa. And so obviously this has the scientific community very excited, because anywhere on Earth where you find water, you find life. So the question is there some sort of life that could have evolved beneath those icy surfaces of Europa and still exist today? So we will be developing an orbiter called Europa Clipper, which will launch in 2022, and then a Europa lander, which will launch in 2024 to actually go down to the surface of Europa after we do the reconnaissance with the orbiter. Europa is a very jumbled, difficult place to land, so we're going to spend a couple of years with the orbiter trying to find the best possible place to land with the lander. This is one of our newest missions. We were just selected for this mission last month. It's a journey to Psyche. Psyche is, I believe, the 5th largest asteroid, and it is a metal asteroid. So it is entirely made of metal. The scientists believe that this was once a small protoplanet, which over time had its surface stripped away by asteroidal and comet bombardment, leaving just the core. So the reason we want to go there is it allows us to explore a planetary core directly, without having to drill through, thousands of kilometers of surface. So we are just now putting the project team together for this mission, and we will be launching that mission in 2023. An interesting fact, if you can imagine an entire metal asteroid, basically the size of the state of Massachusetts, filled with all kinds of metals, whether it's platinum or titanium or iron or whatever. The statistics I have heard is that it is about 100,000 times the entire GDP of Earth. That's what its worth would be if you could somehow mine it and bring it all back. So we'll give you that as a challenge. And then finally, just some of the earth science that we'll be doing. GRACE is our current mission that we use to map gravity around the globe very precisely, so much so that we can tell the difference between salt water and fresh water based on its gravity differential. And GRACE Follow-On is our next generation of those missions, and that is a partnership with the German Space Agency, which will launch, that says August. We've actually had to change our launch vehicle, so we'll probably launch in December of this year to continue that gravity mapping of the Earth. We're partnering with the French on a mission called this one, Surface Water Ocean Topography. We currently measure ocean height with our radar satellites. This mission will allow us to not only measure ocean height, but the height of fresh water bodies, lakes and rivers. We've never been able to do that from space before, but using radar interferometry, we can now do that with this spacecraft. And it's very important for helping us understand the water cycle and measuring what's going on with the water cycle globally. So again, scheduled to launch in 2020. And then another Earth Science mission where we're partnering with the Indian Space Research Organization. This is a synthetic aperture radar mission with S-band and L-band radar. We've never put those two radars on board the same spacecraft. And again, this will be used to measure things like biomass, glacial movement, coastal erosion, and a lot of important attributes of the Earth that we need to fit into our models. And that's a brief run-through of all that JPL is doing. I didn't even talk about exoplanets, all those planets around other stars. We saw the news last week about the 7 planets we found around TRAPPIST-1, the star system there. And that will be a very important part of our future as we look out beyond the solar system, is really ultimately being able to image and spectroanalyze Earth-like planets around other stars. And that's what we're starting to think about right now, how we can do that. So thank you for the opportunity to give you a brief history and update of JPL missions. And I'll turn it over to Susie for a great look at the Voyager mission, which is humanity's first interstellar spacecraft.
All right.
And now Suzanne Dodd, who's the director of the Interplanetary Network, will tell us about the Voyager.
We're going to switch seats here so I can drive.
Yeah.
All right. I don't think anybody would mix us up. Just in case.
Just in case.
All right. Bring that in. Can you all hear me all right?
Yeah.
All right, great. So I'm going to tell you a story, start by telling you a little bit of a story of myself. I am a Caltech graduate. I was happy to give a lot of thumbs up to all the Spaniards involved with Caltech and MIT. But my very first job was on the Voyager project. I started as an engineer working in sequencing, sending the commands to the spacecraft for the Uranus encounter, and in like 1985. And I worked on the mission for the Uranus and Neptune encounter. And then I went off in 1990 and did other things for 20 years. And in 2010, I was invited to come back and be the project manager of Voyager. And it was just fabulous to have the opportunity to come back to Voyager and be involved with such a wonderful mission. I'm going to start with a video, and this is going to kind of bring you up to, the video is going to give you some history of Voyager. It runs for about 4 minutes, and then after the video, we'll talk a little bit about the planetary, but most of this talk is going to be talking about what happened after Neptune. So what have we been doing for the last 28 years? I have to count. So let's see if I can get this going.
knew we were on a journey of discovery when we launched the Voyager spacecraft, but we had no idea how much there was to discover.
This spacecraft, more than anything else, required to be really intelligent and autonomous. It had to diagnose itself.
When I think about Voyager, I think about that it still works, that it ever worked, and that I have in my pocket more memory and computing power than exists on that spacecraft.
They're amazing. They just keep going and going and going.
Voyager really has changed our view of the solar system, seeing things that we had not expected or even imagined. We had never seen active volcanoes anywhere else in the solar system before flying by this small moon called Io. The possibility of a liquid water ocean under the icy crust of Europa. On and on to Titan, where we found an atmosphere in some ways like that on Earth, but much colder and no oxygen. And on to Uranus, where we found a small moon, Miranda, which had one of the most complex geologic surfaces we've seen. And finally, even at Neptune, the most remote planet, we flew by its moon, Triton, the coldest body we visited, 40 degrees above absolute zero, and even there were geysers erupting from its icy polar cap. So it was time after time we were seeing things that we had not imagined, and that is continuing as we reach the edge of interstellar space.
Just the bonanza of scientific information was so overwhelming, but at the same time, the sense that this cultural artifact of our civilization was on its way beyond the outer planets to the open seas of interstellar space. That was the great thrill.
Voyager, I know what you're thinking right now. You're really far away from home. You've seen a lot of things. It's probably very dark and very cold out there. You don't really know where you're going. You don't really know what you're going to find.
Voyager serves as an awesome robotic emissary for our species. You remember Voyager was fully equipped with a record of who and what we are, with the sounds and heartbeats and whale sounds and all the different languages of the world.
Hello from the children of planet Earth.
It's for any alien who would come upon it, they'd sort of know what we're about. I think science does not become part of a society, part of a culture, until it gets embraced by the artists who walk among us. And when you've got poems written about Voyager, it appears in film. It's a little bit of that which we carry with us as humans, where we always want to explore and go a little farther away from home tomorrow than we went today. A little bit of us out there in the cosmos.
Okay, so hopefully that gives you a little sense of awe and inspiration about Voyager, and I'm humbled by this mission every day. I like to do this. Who was born after 1977 that's in this room? Raise your hand if you were born after 1977. Okay, so you guys are younger than the Voyager spacecraft. There are actually two spacecraft. They were launched about 2.5 weeks apart. Voyager 2 was launched first on August 20th, 1977. We're coming up on our 40th launch anniversary. That's 4 decades. Just imagine how old the technology is on that spacecraft. Voyager 2 was put on a slightly different trajectory than Voyager 1, so it got to Jupiter, the first planet they encountered. It got to Jupiter second, so that is why it has the 2 designation, even though it was launched first. I put down some notable facts that were happening in 1977. The Apple II computer had just hit the streets. That was the best in computing power at the time. The original Star Wars movie came out in 1977. There's another series that's still going and going, since there's a movie still to come out. And this is for my Australian colleagues, but the Bee Gees had the #1 hit in 1977. How Deep Is Your Love? So it was mentioned a little bit in the video, but again, the mission was launched in 1977. The technology is 1975. So if you all look at your iPhone, an old iPhone at that, an iPhone 5, you have over 200,000 times as much computing power in your phone than are on the Voyager spacecraft. So your pocket is really carrying a fleet of Voyager spacecraft around as you walk around the streets of Madrid, if you want to think of it that way. Some other firsts that Voyager had technology-wise include it was the first spacecraft to have to diagnose its own problems. It had what we call onboard fault protection, so that if it had an error, it could correct itself without us communicating with it. It also learned from the Pioneer missions, which went to Jupiter before, that there was a lot of radiation at Jupiter, and that was something that wasn't expected during the early development. So they had to redesign the electronics and parts so it wouldn't be affected by the radiation as it flew by Jupiter. The trajectory that Voyager took happens only every 186 years. So we are very lucky to have the technology and the right alignment of the planets, where all of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, were all basically aligned on the same side of the sun. So you could take a mission and you could go by Jupiter and use that gravity assist to get it out to Saturn, use that gravity assist to get it to Uranus, and then out to Neptune. And so every time it goes by one of these gas giant planets, it speeds up. And right now, Voyager 1 spacecraft is going at about, I'm going to put this in miles, and I apologize for you, but it's about 38,000 miles per hour. Voyager 2 is slightly slower. But you can see the dates, the launch dates, and the trajectory here. Voyager 1 completed its initial mission, Jupiter and Saturn, and the trajectory it was on took it up and out of the plane of the planets. Voyager 2 then could continue on. Since Voyager 1 was successful at Saturn, Voyager 2 got to continue on to go to Uranus and finally to Neptune in 1989. So that's 12 years after it launched is when it finally got to Neptune. And just a little bit of the comparison. And 1 astronomical unit is the distance between the Earth and the Sun. So Jupiter at the time was very far away at 5 astronomical units. You double that to get out to Saturn, double that to get to Uranus, and then add 10 more and you're at Neptune. The primary mission when it was launched was for Jupiter and Saturn. It was designed, the level 1 NASA requirement was for a 4-year mission. Okay, we're now reaching our 4th decade. And it's due to a lot of great proposal writing to keep getting funding. So, but being designed for Jupiter and Saturn, when you get out to Uranus and Neptune, it's very dark. And so we had to make adjustments in our onboard algorithms in order to be able to take pictures when it's very dark. And we created something called image motion compensation. It's similar to trying to take a picture out your car window and not have everything smear. You move the camera to track the object you're looking at, and that's software that we created as the mission was heading toward Uranus and Neptune. We actually changed the onboard software to be able to improve the science data we could get back. So how do we talk to Voyager? Well, we need what's here just outside of Madrid. We need the very large antennas of the Deep Space Network. And this happens to be the 70-meter antenna that's about, how far, an hour away? Hour drive? 45 minutes, yeah. I was just there for the first time yesterday. Very exciting. But Voyager and all planetary spacecraft rely on these large ground antennas that are run by NASA and the Jet Propulsion Laboratory. The data rate of Voyager is tiny, 160 bits per second. It's just like a tiny little drop. Distance-wise, at 20.6 billion kilometers for Voyager 1, it takes the signal over 38 hours to go from the Earth to the spacecraft and back again. So the one-way light time is over 19 hours. I like to tell people that if I come into the office in the morning and I send a command to Voyager to say, good morning, Voyager, how are you doing? I'll get a receipt of that command. Voyager will say, hi, Mrs. Dodd, how are you doing? I'll get that on Tuesday afternoon. So it's like a day and a half later for a round trip. That has its challenges when it comes to commanding the spacecraft. What we've done with Voyager is all the routines are on board. It automatically just kind of loops through regular routines, regular calibrations of the data. If there's any emergency, the spacecraft really has to be able to put itself in a safe state and manage it so that it doesn't get too cold, it doesn't pointing doesn't start drifting off and things like that, because it's going to be a while at that round trip light time to be able to recover the Voyager spacecraft. So the spacecraft itself has to be very autonomous and has to kind of take care of itself until we can. Plus the data rate is very low, so we're not going to get a lot of information back. So it takes a while if we were to ever have an anomaly to recover. But knock on wood, it's been very, very healthy. So what has Voyager been doing since 1989? Well, it's been on what we've renamed the Voyager Interstellar Mission, and that's a mission to measure the environment as the spacecraft travels outward from the sun, away from the planets. And what's out there, the area around the sun is called the heliosphere. That's the area where the charged particles from the sun affect the environment and affect that local space around the sun. And I think you've probably seen videos like this. I can get it up. Here we go. This is just going to show you some solar flares that come off, and you can see that the sun is always spewing off material, and it's those kind of outbursts of charged particles and hot plasma that Voyager is measuring as it drifts away from the sun. And here, another illustration just shows you a little bit more. There we go. So the sun is sending out charged particles, but it's also traveling around in the Milky Way. So it does hit this interstellar flow of material, which causes what we call the heliosphere to not be spherical, but more comet-shaped, elongated. And we are very fortunate in the case for Voyager that our two spacecraft are going toward the nose of that comet. They're not. If they were going toward the tail, we would never reach interstellar space. Interstellar space is defined by the area outside of what's labeled here as the heliopause. So that's where the charged particles from the sun are no longer felt, and that's kind of the goal. That's the big milestone or touchdown that Voyager is looking for, is to cross into interstellar space. And this is just an image showing that all stars have astropheres. This is an example. This was actually taken by the Spitzer Space Telescope. But that star in the middle, you can see how the red material is around it in a bubble. That's an example of an astrosphere, like our heliosphere, around another star. Okay, so it's very hard to get out in space yourself, but you can do an experiment in your kitchen sink that emulates what it's like. So when the charged particles from the sun are expanding out, at first they're supersonic, and then they cross what's called the termination shock, and they go to subsonic. Voyager 1 crossed the termination shock in 2004, and Voyager 2 crossed it in 2007. And then eventually, you'll cross out of the heliosphere, across the heliopause, where all you'll be measuring is charged particles that come from interstellar space. In other words, they come from other stars, explosions and supernovas of other stars. But if you're in your kitchen sink, turn the sink on, or turn the water on, rather, and you can see it kind of running, and you can see where the initial water coming out would represent the solar wind, the ridge that's formed represents the termination shock, and then the outside part is interstellar space. So now you have a science experiment you can do at home. So we've been traveling since 1989 looking for the heliopause. I think it was further out than anyone ever expected. It's definitely further out than NASA expected. There's been times in the past that NASA thought they should just cancel the mission because it didn't seem like it was gathering any real interesting information. But we survived those budgetary threats, and in the summer of 2012 was the first time we actually saw some data that made it look like we were on the edge of the heliopause and on the edge of interstellar space. So the upper chart shows you that the cosmic rays that travel fast from interstellar space were increasing, and at the same time, the slower ions coming from the sun were decreasing, and you could match up the decreases with the increases. And then very abruptly, on August 25th, 2012, all the particles from the sun disappeared, and it's been flat like this ever since. And that was the first look that scientists had, thinking that, well, we might be in interstellar space. The charged particles tell us we're in interstellar space. But we needed more information to verify that. And we got very fortuitously some information from our plasma wave science instrument. And what the plasma wave science instrument does is it can measure vibrations and frequencies. And when a solar flare leaves the sun, it excites the plasma that it's going through. And out in the material that's closest to the sun is hot, and then the further out you go, it gets cold. And what Voyager 1 saw, there was a solar flare in March of 2012 that took over a year. It took about 15 months to travel at the speed of light out to where Voyager 1 was. But in April of 2013, you see this big red excitation point where we were able to measure the frequency. And you can hear the difference in the frequency here. Again, let me put the video. Oops. Go back. There we go. Oh, every time. Maybe not. There we go. So it's a higher frequency, and scientists were able to trace back along the dotted line to basically to trace back and say, well, if I went backwards, I could say that I had crossed interstellar space at the same time that we saw the particle data change. And again, I sort of mentioned the theory, but the solar plasma gets colder as it gets further from the sun, but then you see a large increase when you're in interstellar space, and that's what scientists believe was happening. And they had a big debate. I mean, Ed Stone was out there arguing with all the other scientists, and they kind of had a big debate about whether we were really in interstellar space or not. And it took them a year to decide that. So the data today, if you look on the top half of the colored chart, the data on the left starts with the heliopause crossing August 2012. The first excitation periods. We had another one in November 2014, a big event, and then one in November 2015, also a big event. And you can see where the frequency rose up, but then it flattened out, which is very similar to this theory. So Voyager 1 is in interstellar space. It's what you call the local interstellar medium. It's not very far into interstellar space, but it's there, and it continues to take data, and it tells us what the environment is in interstellar space versus what the environment is under the sun's influence. So the question then is, what's happening with Voyager 2? I like to tell people that anybody can make a model fit to one data point, but it's hard to make the same model fit to 2 data points. So it's great that we have 2 spacecraft. It's great that they're in situ. They're actually there measuring the data. So the red lines represent Voyager 1 and the cosmic rays coming from outside of our heliosphere. And right about when we first started seeing issues with the particles was back in, kind of between 2011 and 2012. About a year before the heliopause, you can see that it starts ramping up, and it really started ramping up right there in 2012. So the blue line, though, is Voyager 2, and it's just kind of moseying along. It may be getting there. We see that it took a steep rise in 2015, but then it dropped back down again. So, and when you look at the data between Voyager 1 and Voyager 2, they don't look the same. The data has the Voyager spacecraft are crossing the outer regions of the heliosphere. They don't look the same. Voyager 1 is going up and out of the ecliptic plane at about a 35-degree angle. Voyager 2 is going down and out of the ecliptic plane at about a 43-degree angle. So they're not, one's going up and out, one's going down and out. So they're not crossing at the same time or the same place. And if you recall, solar cycles happen about every 11 years. You'll have a solar cycle where there'll be lots of solar flares, and then it will come back down again. So on this image, if you look at the bottom Voyager 1 bar, we crossed the termination shock in 2004. We entered interstellar space in 2012. It was at a solar minimum. We are now coming back into a solar minimum. So we're hopeful that Voyager 2, which crossed the termination shock in 2007, and it's been in the heliopause region longer than Voyager 1 has been. But we're hoping that in a year to maybe 2 or 3 or 5 years, we'll also cross into interstellar space, and then we can say we have 2 spacecraft to cross into interstellar space. Voyager can continue operating for likely another 10 years. Probably about 2020, we have to start turning off instruments. There's 5 on basically on each spacecraft, and our limiting resource is power. We use a nuclear power source, and it's decreasing at 4 watts a year, and eventually we just don't have enough power to operate instruments. But we think we can have the last instrument at least go to 2025. My personal goal is to operate Voyager for 50 years. So all those 70-meter antennas need to hang around for another decade. It's really been exciting to be part of this mission. So Voyager will continue on, as we said, even when it's done taking scientific data, it still is going out of the solar system and out into interstellar space, and it will be circling around the Milky Way galaxy, and it has that gold record on it that will then be circling around the Milky Way galaxy with a picture of what our planet looks like in 1977. So the aliens will be all into disco and everything when they find the Voyager spacecraft. But with that, I just want to say thank you to the Academy for letting us give a talk today. And Madrid is a wonderful place. Spain is a wonderful place. I'm hoping to spend more trips here. But certainly the Deep Space Network has made Voyager what it is today. And Ed Stone likes to say, Ed Stone is our project scientist, he likes to say that the DSN and Voyager grew up together. A lot of enhancements were made at the Deep Space Network, especially for Voyager. And without the Deep Space Network, certainly during the planetary encounter, but now especially without those large antennas taking the data, we wouldn't have a spacecraft in interstellar space. So I want to thank you all. And thank you for giving me the opportunity to talk.
Thank you very much. Now the floor is open for questions or comments from the audience. Any questions or this one there?
Hello, good afternoon. Hello? Hello, good afternoon. Thank you very much for your speaking, for your presentations. They were very interesting. So I wanted to ask Mr. James about the exploration of the solar system and about the recent discovery of the planets in the TRAPPIST system, because they are orbiting a very small star, and therefore they are very close to each other, these planets. How would affect our exploration of the solar system, if we live in TRAPPIST-1 with planets as close as they are?
In other words, if we tried to explore TRAPPIST-1, how would we do that? Is that?
Yeah, exactly.
Well, the nice thing is they're close together, so you could get much data very quickly on all 7 planets, right? But really, it's interesting because there's developing this whole new science of comparative solar system formation, if you will. So 20 years ago, we didn't even know if planets existed around other stars. We had some evidence perhaps that they did, but we really weren't sure. Now we can see a variety of planets around a variety of stars. And if you think about it, most of the observations we have today are from the Kepler spacecraft, the Kepler telescope, which looks at a very small piece of the sky. And yet we're now up to, I think, 22 planets that we've found in the habitable zone and over 3,000 planets that we have confirmed using Kepler data and some Earth telescope data. And that's, again, a very narrow field. So the belief is that most star systems now have planets. That's kind of what the scientists believe. So now as you start to see those planets around other stars, just like the TRAPPIST-1, very unique, right? It's a small, very dim star, and yet these planets are at a position that the temperature would be about right to allow water to form. Now they're orbiting every like 3 or 4 days, so that kind of creates some problems, I think, in life forming, perhaps. But just the ability to use our telescopes to find those planets, number one, and then in the future, NASA's objective is to be able, as I said, to image those planets and do spectroscopy on them so we can understand, is there oxygen there? Is there hydrogen there? Is there nitrogen there? And then if you can measure those, if they exist without any life, they have a certain percentage. If there is life going on, that percentage changes, and we can determine that, yes, something is happening on that planet, that there is life there. So I think in the next 20 to 30 years, that's going to be the very exciting field of astronomy in astrophysics, is to find those planets that are Earth-like and find out what they're made of, and perhaps there's life there. So it's a very exciting time. So if you were born after Voyager, you'll get to see that. So, but yeah, very exciting.
Any other questions? Well, I have one for Susie from a very ignorant perspective. You said that originally the Voyager was planned for a few years, and now it's going to last decades. Was it designed originally to last decades? Who had the vision to make it last
I
decades?
think it was originally designed to last 4 years. The prime mission was Jupiter and Saturn. Now I've been told old stories, reunion kind of stories, that the engineers, when they got a chance to put in a more, when their bosses weren't looking, they would take a part that would be more robust and stick that in. They had a vision to make it last much longer. They knew they could get to Uranus and Neptune because of the trajectory. I don't think anybody thought it would last, especially two spacecraft, to last 40 years. But they did work hard behind the scenes to make the spacecraft as robust as possible.
It was good vision.
Yeah.
Okay, anybody wants? There's a person there.
Okay, thank you for your talks. Just one question for you, for Susan. Have you computed the trajectories of the two Voyager spacecraft for the long future?
Have we computed the trajectories? Yes.
Where are they heading to?
For the long future. Well, yeah, I can tell you that Voyager 1 will pass within 1.6 light years of a star called AC7 plus 79 in 40,000 years. And Voyager 2 gets within about 4 light years of Sirius, and that's going to take it something on the order of 250,000 years. So we know where they're going, yes. But it's not likely that
we will get there.
Well, it's not likely that it will. Space is very empty, so it's not likely that we'll encounter another planetary system.
Any other questions? If not, well, I want to thank you very much for coming to the Academy and giving us these presentations, and we are hopefully seeing you again in your next trips to Madrid. Yep. We'll be welcoming you to interact with our audience.
Yep. Great. Thank you.
Thank you
so much.
Thank you.
Thank you, everyone.
It was very good.
We are partners with CAB. I was at CAB today, this morning.
Last week I delivered the chips for the Meta.
Oh, yes. In fact, they told me that. Yeah, so very important milestone.
Oh, yes.
Yes, yes.